Okay, hi everyone. Uh, we are going to talk. So I want to pause. We started diving into the cross product stuff. And then I realized, especially when I was looking at assigning the homework, that I always give this spiel about lines and planes, and it's actually the right time to do it is when we're talking about the dot product. And it'll also come up with the cross product. So I want to give my little spiel about lines and planes. And then I also want to talk about projections, which is on that handout. It's the one of the after the cross product stuff. There's some stuff about projections. So those are the two things I want to talk about today. Oh, any logistical questions or anything before we dive in to the math? No, you're pumped, ready to go? All right. So, okay, so lines and planes. In particular, I want to talk about equations of lines and planes. I'll start with lines because it's 2D, it's easier to see everything in 2D, and then we'll kind of generalize to 3D. That'll be about planes. So let's start with 2D. So tell me an equation you know for lines. What's your favorite line equation? Like, what's your favorite general form? What do you always say? Y equals mx plus b, right? So you know y equals mx plus b, which is the sort of slope-intercept form, because m is the slope and b is the y-intercept, right? When you plug in x equals 0. Another form? Point slope. Point slope is what? Y minus y naught equals m times x minus x naught. So x naught comma y naught is a point on the line. Okay. So those are the two ones that you know the best, right? One thing I take issue with these two formulas is they're biased. They're biased against one type. There's a type of line that does not appear in these formulas. There's a type of line that's discriminated against. What kind of line? Anybody? Yeah. Vertical lines. Sorry, you're gonna asking me to clarify what I was talking about. Seems to be my teaching style is ask vague questions and hope someone divines my intentions. Yeah, so vertical lines, right? So this misses vertical lines, which, fine. If you're talking about functions, y equals a function of x, that's fine. But if we're talking about geometry, it's nice to have vertical lines. So these are two forms that you know. But also, there's some more general forms that include vertical lines. Because both of these involve a slope, so you can't have a vertical line because the slope becomes like infinity, right? So the easiest one is just to say something like the following. Ax plus by equals c. It's nice because it's symmetric in x and y. Like if you switch x and y, they don't, So that's why you can tell. So like, for example, here, what's the equation for a vertical line in general? X equals constant, right? So here, if b is 0, then I get, b equals 0, vertical lines. A equals 0 would be a horizontal line. And otherwise, you can sort of solve. I mean, I guess it includes horizontal, but you can sort of solve for y, and I think the slope is probably minus, what is it, minus a over b or something like that. Slope of this line. And so that's one way to do it. But there's also like, I could do something even a little more general, like a version of point slope, which is something like this. because this doesn't really tell you a point that it goes through, you'd have to find an x and y satisfying this equation, right? But if you do something like this, that's something that definitely goes to the point x naught comma y naught, right? If you plug in a specific point here, that'll give you 0. So yeah, x naught y naught is on the line. But the question I guess I have is, what do the a and b really represent? The one reason we like these forms is we understand what all the letters are doing, right? M is the slope, and so on. But here it's like, well, what do a and b mean? I mean, you can, like we said, you can sort of solve for the slope in terms of a and b if there's a slope. But let's think about this. So what does the pair a comma b represent geometrically? So that's one reason probably you haven't seen these, you don't see these forms as often. But I claim it has a really nice interpretation. So let's do an example. Let's say I have the line x plus 2y equals 4. Okay. That goes through, I picked this because this goes to the point 4 comma 0 and 0 comma 2, right? Is that half of that? Maybe a little higher. So that's this line right here, I think. Tell me if I'm doing something wrong. It's always possible. Okay, and we have, but the coefficients are 1 and 2, right? What's the slope of this line? -1/2. Do you remember the slope of a perpendicular line? Do you remember, like, if a line has slope, it's the negative reciprocal? Right. So actually, if I think about perpendicular, that would be slope 2, right? And here's what I claim. And I mean, I'll give you a good reason why. But just in this example, if I pick any point on the line and I draw a perpendicular vector, so there's a 1 right here. Do you believe this, that 1i plus 2j is perpendicular to the line? Because here you go over 2 down 1 for the line. In this vector, you go over 1 up 2, right? Do you agree with that, that over 2 down 1 is perpendicular to over 1 up 2? Okay, so look, so that's actually, so I'm saying this is not I'm claiming this is not a coincidence that, so the claim I have here is that AI plus BJ is perpendicular to the line. Actually, it has a name. It's called a normal vector. One thing that's going to be sort of silly in this class is that there's like 3 different words for perpendicular. There's perpendicular, there's orthogonal, and there's normal. And they all basically mean perpendicular. You could argue in certain contexts, certain words are more appropriate. But anyways, this is called a normal vector, right? Does that make sense? Why is that happening in general? So I'm claiming this is true in general. It works in this example, certainly. I think if you look at this form, you can see why it works in general. So why in general? Why does this work in general? Well, if I draw some line, let's use the a times x minus x naught plus b times y minus y naught equals 0 form. So now I have some line in the plane, and it goes through the point x naught, y naught. And there's some other point. I mean, one way to think about this is if you think about why does point slope work, right? Just going back for a second. Point slope works because if I divide this over here, there's a point, you have a delta y over delta x. So an x comma y satisfies this if and only if like you can plug it in and get the right delta y over delta x. That's kind of why point slope works. Well, now think about this, x minus, so if I have a point here on the line, x comma y, well, there's a vector. There's a vector right here. And what is that vector? What's the x component of that vector? What do we do if we have a vector between 2 points? Just subtract, right? So this is x minus x naught I plus y minus y naught j, right? So this is along the line. Is a vector parallel to the line. Okay. And here's where something cool happens. There's something you start to notice in math, especially once you learn about dot products. I claim this is a dot product. I can sort of factor this as a dot product of two vectors, right? Because two vectors, you multiply components and add. So how could I factor this as a dot product? What's the first vector? You guys get what I'm getting at all? No. I'm saying anytime you see like product plus product, you could think, oh, that's actually, I could interpret that as a dot product, right? Something times something plus something times something. And if I do that, so I'm saying like recognize dot product here. This equals this vector dotted with this vector, right? If you just multiply this out, if you just dot this out, do you agree that you get the left-hand side there? Okay. Does anybody see where I'm going with this? We're claiming that AI plus Bj is perpendicular to the line. Why? Why does this sort of show that? Yeah. The dot product now is 0. And what does it mean when the dot product is 0? Perpendicular, right? So it's kind of cool, like, so that we could rewrite this equation as, i.e., a times x minus x naught plus b times y minus y naught equals 0 is the same as like I just wrote it over there, but it would be nice if I was on Notability and I could just copy and paste that. But and so yeah, which means this vector is perpendicular to this vector. And this vector was along the line, right? This vector is parallel to the line. This is parallel to the line. So this is perpendicular to the line. And that's kind of neat. That's kind of a neat way to think about this. Like the coefficients, if you write a general line equation like this, the coefficients actually give you a normal vector to the line. So we often use the letter n for normal vector. N is AI plus bj is normal to the line. Again, normal is a synonym for perpendicular. Okay. Does that make some sense? Okay. Yeah, so I like this. This is kind of the most generic equation you can get for a line. And the A and B mean something now. They mean something vector-wise. And now, this is super useful if you go up a dimension to planes. Okay. So if we go up to 3D, maybe I should be drawing the n in here. Like, see, n is right there. Like, right. So perpendicular line, parallel line. Okay, let's go up to 3D. And talk about planes. So if we generalize this equation to 3D, it's really, maybe I should leave this equation right here. Because we've sort of seen that if you have z is like a linear function of x and y, then that's a plane, right? But I could rewrite it this way. So like, let's go up to 3D. So if we have ax plus by plus cz equals d, or by the way, this is also, there's a similar like line of thinking here. When we had z equals a linear function, that gave us all planes except vertical planes because those had slopes, right? There was like an x slope and a y slope. But if I want vertical planes, this is a better formula because like if b and c are 0, then we get x equals constant, which is a vertical plane, right? Or if a and c are 0, we get y equals constant, which is a vertical plane. So a times. So the generalized form is this equals 0. Because this is a plane containing the point x naught comma y naught comma z naught, right? So I'm just writing the I'm just adding the variable z to get this. So these are sort of general plane equations. But I can do the exact same thing I did in 2D and recognize this as like a dot product, right? Recognize as dot product again. So this is really the same as, again, it's sort of an unnatural thing to do, you know, to factor something as a dot product, but it just becomes a trick up your sleeve. And certainly when I write this down, you can verify that when you dot product it together, you get back to this equation, right? Yeah, kind of exactly the analogous thing there. And if we draw a picture of what like a plane in space, right, it's always kind of hard to draw. It's a plane, it's supposed to be some plane in space, right? And here's our given point x naught comma y naught comma z naught. It's that point. And if we have another point on the plane x comma y comma z, then we have this vector like that, that's sort of in the plane, parallel to the plane. And that's going to be given right here. So sometimes people write this as like, I could have done this up there too, as like x minus x naught vector. So the x vector stands for x, y, z, and the x naught vector stands for x naught, y naught, z naught. And this is parallel to / in the plane. Right? And now what this equation is saying is that the vector ai plus bj plus ck is perpendicular to this vector in the plane. So in fact, we have this vector shooting off here, perpendicular, n, which is given by the coefficients. Right? So this is n. And again, sort of like a point x, y, z satisfies this equation if and only if it satisfies this dot product equation. And that means if a point, like if a point's on the plane, if and only if the vector from the given point to that point is perpendicular. And that should make geometric sense. Like that's one way to determine points in this plane is all the points that like, if you draw the vector from the given point to that point, you get a vector perpendicular to this vector. You can think about a plane as all points perpendicular to a given vector. If that makes sense. Through a particular point. I guess there's different planes perpendicular to the same vector. But if you pick a specific point for it to pass through. Right, so so sometimes you actually see, I think the book actually writes like, this is kind of the general vector form of a plane equation, but it looks kind of daunting until you tease out what it actually means, and it's just a way of writing that. Make sense? So it's kind of weird, but again, let's do an example. Something that we can definitely picture. So how about the plane like x equals 4? So remember, down there is the x-axis. Down here on the bottom of the front wall is the y-axis. Vertically is the z-axis. So the plane x equals 4 is actually, like if I put a wall between you and me, I really should have a wall separating me from the masses, you know. What? No, I'm just kidding. So x equals 4 would be a plane like this, right? I could rewrite this in that form. I mean, it's sort of silly, but we could rewrite as 1 times x minus 4 plus 0 times y minus 0, say. Let's go through the point. This contains the point 4, 0, 0. I'm gonna run out of room. Let me write that down here. 1 times x minus 4 plus 0 times y minus 0 plus 0 times z minus 0 equals 0, right? It's a very overwrought way to write the equation x equals 4. But you can read the normal vector off of this now, right? What's the normal vector? Once I have this written down this way. Yeah, just 1i plus 0j plus 0k, right? So n equals 1i plus 0j plus 0k, or really just I. And does that work? Is that true? This vector right here, that means plane right here. What's the normal vector to a plane perpendicular to the x-axis? Do you agree that I is a perpendicular vector? Yeah, so it does work. It does work. And yes, I is perpendicular to like any plane, any YZ plane, any plane parallel to the YZ plane. I guess I could have even done this plane x equals 0 and just had 1x plus 0, I plus 0, you know, parallel to the YZ plane. So that's just a, you know, a sanity check that this actually does make sense with stuff that we're used to, right? Cool. So now anytime you see a plane equation, most plane equations are going to be written like this. And you can just identify, and if it's not, you could always get all the variables on one side, kind of like we did with the functions of 3 variables, level surfaces type stuff. And then once you identify the coefficients of A, B, and C, that's your normal vector, right? And the coefficients of X, Y, and Z. I don't know what I just said. That's how you identify your normal vector. Good. Okay, so this is cool. I like this because like on the homework, there's going to be questions like write down the plane through this point parallel to this or stuff like that. So now you can do it. All right. I'm going to switch gears and talk about projections, but I will say that there's we're going to use the cross product here too, because maybe I'll just go ahead and say this so we can do it sort of on Monday correctly, but before I move on to projections. But like, if you want to determine a line in 2D, what information do you need to find a specific line in 2D? A slope and a point, right? A point and a slope. What else could you use to find a line in 2 dimensions? 2 points, right? 2 points make a line. And if you have 2 points, you can find the slope, right? How many points do you need to determine a plane in 3 dimensions? 3 points, do you agree with that? 2 points would get me like, to some extent, but I could still rotate the plane around those 2 points. So the third point would sort of fix. And one thing we're gonna wanna do is like, if I give you 3 points in space, find the equation of the plane that contains those 3 points, which seems like it could be kind of daunting. But again, I'll just put this idea in your head. That's supposed to be a plane tilted in space. If I have 3 points, well, 3 points gives 2 vectors, right? I could find these 2 vectors in the plane. And if we want to write down an equation of a plane, we've just said what we really need is a normal vector. We really need a vector perpendicular to the plane. But I have 2 vectors in the plane. How can I use those to get a vector perpendicular to the plane? Cross product. So I take my 3 points, I make 2 vectors, then I cross them, and I get a normal vector. And as soon as you have a normal vector and a point, you can write down the equation of the plane. So it's kind of nice, actually. You can actually write down, if I give you 3 points, you can write down in the equation of the plane. You can do this process. Use 3 points to make 2 vectors, 2 vectors, cross product to make the normal vector. Normal vector plus point gives you the equation of the plane. Cool. You didn't know how to do that before today, probably, right? If I just gave you 3 random points in space and said find the equation of the plane containing them. Okay, good. Hey, you learned something. All right, I'll do this properly on Monday, but I just want to go ahead and say that. That's sort of one thing we're going to do with cross products, is use it to find planes. Okay. Oh, actually, maybe I'll bring the screen down because I can pull up the handout. So the other thing that I want to talk about that's the dot product is useful for, the other geometric thing, are called projections. Which does turn out to be a pretty physicsy concept, but it's also just useful in sort of general geometric senses. So let me pull up. Take a minute to yourselves while I'm pulling this up. We're about halfway through class. Yeah, let me share screen here. Hold on. Yeah, okay. So this was the handout. We were doing cross product stuff on Wednesday. And we'll come back to this. I definitely want to talk about like these sort of general facts and a few of these things about there's geometric definitions of the cross product. But projections turn out only to deal with the dot product. So So I want to kind of like talk our way through these. But let me say a little bit about what a projection is. So this is page 4 of the handout here. I'm gonna pull it up, but yeah, let me talk a little bit about what projections are. Okay, so projections. So let me just start with a kind of a simple example. Here's a vector, 3i plus 7j minus k. Okay. That's a vector that sticks out in space some way, right? Over 3, 7 this way, 1 unit down, so it's pointing. I don't know. You can try to picture how it points. But in particular, we can think about, you know, you actually did this a little bit already about resolving a vector into components, right? And this already is. You have the x, y, and z components. But notice, if you want to sort of like project v onto, say, the x-axis. Well, we already know it's like the shadow. It's like if I shine a light sort of perpendicular to the x-axis, you're going to see the vector. And what you're going to do here is you're really just going to, it's just going to be 3i, right? You're just taking the x component. It's like the component, or an equivalent thing, a sort of equivalent thing is to say, or the component of v in the x direction. And you get 3i, right? And okay, that's like completely uncontroversial. But it's worth noting, one reason I, j, and k are so nice is that they're all mutually perpendicular. And because of that, I can actually think of 3, if I just want to focus on 3i, it's actually perpendicular to 7j minus k, right? So you get 3i, and then note the leftover 7j minus k is perpendicular to the x-axis. And so this is called like resolving a vector into a parallel piece and a perpendicular piece. Like if you have some direction you want to think about, you know, a lot of times it's going to come up in physics with like, oh, I've got a force, or I've got something that's traveling in this direction and there's a force in some other direction, and I want the component of the force in that direction. Then that's, yeah, so we sort of, so maybe you only care about, maybe you're sliding something along the x-axis, but there's a force pushing it in that direction. But all you care about is the x component of the force. So you got this part of the force that's contributing to the movement, and this part of the force that's not, because it's perpendicular to the movement. Does that make some sense? Okay, I don't want to get too physicsy in this class. It's supposed to be a math class, but yeah, so we sort of resolve v into two pieces. One parallel to the direction we care about, and one perpendicular. That direction. So the piece that's parallel is called the projection. The parallel piece is called the projection. Okay, and yeah, in cases where we already have, we're trying to go parallel to the x, y, or z axes, it's trivial once we write the vector down. But what if I want to project onto some other line, some other direction? That's really the question here. So that's like a kind of overly simple example, but like, Let me give you a little bit of a harder example. Let's say I had the vector, let's just do this in 2D at first. Let's project V is, let's do I plus 5j onto the line through the origin in the direction 4i plus 3j. So I'll draw this through. So, okay, so here's, if I go over 4 up 3, well, let me do this. So 1i plus 5j is some vector like that. So there's your v, right? Oh, let me give this a name. Let's call this w. Okay, so that's our v, is something like 1i plus 5j. Our w is some line like that, containing the vector w. See what I'm saying? And then the projection is going to be colors of chalk here. So the projection is going to be like that, kind of like, you think about shining a light perpendicular, like far away, perpendicular to this line. Then the projection is going to be like that vector right there. So this is the projection of V onto the line given by W or something like that. Does that make sense? That's what I'm looking for, is the projection. Yeah. Oh, this. Yeah, sorry. So that's, so this, yeah, right. So you do get like this right triangle here, right? Good. And then by the way, actually that's kind of good, because this vector right here is actually the other component, the perpendicular piece, right? I'm sort of resolving V into a sum of two things, one parallel and one perpendicular. So the book uses terms like this, like calls this like V parallel. And then this is like V perp, or perpendicular. So when I was talking about resolving into two pieces, these would be the two pieces, one parallel to W and one perpendicular to W. Does that make sense? At least like conceptually what I'm asking for. Now the question is, how do we actually do that? And here on the handout, I actually sort of walk through this. Oh, maybe I should have done this example, but oh well. Just follow this example before class. Doesn't really matter. So one thing people often do, you want this vector. You want to know what this vector is. So you want to know its length and its direction. Do we know anything about either of those? Do we know its direction? Yeah, we do. It's the same direction as W, right? So it should be parallel to W. So it should be some scalar multiple of W, right? So that's the first thing. But then the real question is, how long is it? I'm going to go ahead and say this, though. What's helpful is to scale W to be length 1, because that's going to not having it be not length 1 kind of messes you up, because it's really, because now you have to care about the length of W. That's why I talk about the usefulness of unit vectors, is like if you're just trying to specify a direction, which is what this W is doing. Like if I said, 4i plus 3j, or I said 8i plus 6j, it's the same question, right? It doesn't change the question if I or 40i plus 30j. It's the same question. I'm looking for the same vector. So it's helpful, let me just say, it's helpful to scale W to be a unit vector, length 1, because it doesn't really matter. And so here, the magnitude of W is the square root of 4 squared plus 3 squared, right? It's my favorite example of a vector that you're going to scale to be length 1 because 3, 4, 5 is a Pythagorean triple. So let's set U to be 1/5 W, which is, so U is 4/5 I plus 3/5 J. And that's a unit vector. So actually what I'm really looking at here is, I really have this right here, which is sort of U. Okay. So let's not think about W, let's just think about U now. And now I want to look at this. So I want to look at this picture and think about how to find the length of this side of this triangle. And maybe I'll redraw the triangle, more just like a flat right triangle. So let me just like tilt your head so that U is horizontal. Because we'll come back to the specific we'll come back to the specific example, but let's kind of try to do this in general. So let me redraw. So let's just make a horizontal line. Let's make U length 1 right there. What was green? And let's make V like that. V like that. And then, like I said, we have the parallel, the projection, and then the perpendicular. Right, so this is the projection. V parallel. And this is V perpendicular. Okay. I want to use some geometry to figure out the length of this vector. How do I use triangle geometry to figure out lengths of sides of? What length would we know here? We know the hypotenuse, right? So what's this length? This length right here is magnitude of V, right? Or it's important to think about the difference between a vector and its magnitude. So if you want to actually talk about a distance, it's magnitude of V. Well, if I call this angle theta, the angle between U and V theta, then what's the base of the triangle? What's the length of the base of the triangle? What do you multiply the hypotenuse by to get the base? Cosine, right? It's adjacent over hypotenuse is cosine. So the base, let's draw this here like this length. The base is the magnitude of V times cosine of theta. That should look kind of familiar. Yeah. Right, it's called V perp, but it's really perpendicular to U. It's perpendicular to V parallel. You're right, the notation's a little bit. No, it's a fair point. It's not perpendicular to V. It's perpendicular to V parallel. The V parallel is a projection. So we're just writing, I mean, you can sort of write V is V parallel plus V perpendicular, right? And that's the resolution into components that are parallel and perpendicular. Okay, so the base is magnitude of V cosine theta. We've seen magnitude of vector times cosine theta before. Where have we seen that? Dot product, right? we have two vectors in this picture, v and u. What's their dot product? Note, v dot u is the magnitude of v times the magnitude of u times the cosine of theta. What type of vector is u? Yeah, it's a unit vector. So this is really a 1. So in fact, this is a great use of the dot product right here. It's the length, the u dot v is actually this length right here. It's a number, it's this length. So this is a 1. That's 1. So the base of this triangle is really length v dot u, which is kind of amazing. It's like, it's actually dot products are used in projections a lot because of this, and used in like, yeah, just various places in physics and stuff. A lot of it has to do with projections. So yeah, that's equal to that. And so in fact, v parallel, so v parallel is a vector of length v dot u. Remember, this is after scaling u to be a unit vector in the direction of u. So that's kind of amazing. It kind of works out perfectly. The cosine theta is kind of perfect there. And that means you can really just write down v parallel. How do I write down a vector of a certain length in a certain direction if I know the direction and that's a unit vector? Maybe we should go back to this specific example. Right, let me go back to this specific example before I write the general formula, because you can write the formula for v parallel here now. But before I do that, let's go back to this example. So let me just rewrite this as u 4/5 I plus 3/5 j. So I'm erasing the picture, but you have the picture basically down. What is v dot u here? Someone tell me. I picked a nasty number. I didn't quite get an integer, did I? Yeah, 4/5 times 1 plus 3/5 times 5. So 4/5 plus 3, 19/5. I mean, it's basically 3.8. Yeah. And so what is the vector in this direction of this length? How did we take, I've asked you this before, if I give you a unit vector and I want a vector in the same direction of length 3, what do I do to the unit vector? You just multiply by 3 because u is already length 1. So to make it length 3, we just multiply by 3, right? i.e., then v parallel is 19/5 times u, right? Because it's in the same direction as u. v parallel is parallel to u. And then we could write that down here in this example. It's 19/5 times 4/5 I plus 3/5 j, which is something slightly unpleasant, which is why I should have used the example on the handout, because I think that's actually a better, like the numbers work out more nicely. 19 times 4 is 76 over 25 I plus 57 over 25 j. I wish I had the picture still. If you draw it carefully enough, you could probably convince yourself that like if you drew this on graph paper and actually tried to draw the perpendicular, you could probably convince yourself that you end up on something a little bigger than 3i and a little bigger than 2j. Did I do those multiplications right? I don't know. But then that's the actual that's the vector. And then, so in general, it's kind of a goofy looking formula, but V parallel is just V dot U in front of U. And that's where you have to parse this correctly, but it's kind of like this. Remember, this is a number. This is a scalar. So it's a scalar multiple of U. So when I write V dot U, U, I mean a scalar times a vector U. So this is a vector, right? And this is the formula for V parallel. And then we have V is V parallel plus V perp, right? In that picture. And so V perp, the perpendicular piece, is V parallel, I'm sorry, V minus V parallel. So you can write that as a formula too, V minus V dot U, U, right? And now I wish we had another couple of minutes, because if we did, I would actually find out what V perpendicular was here and check that it's perpendicular to this, which you could do. You should do on your own time. Check the example. Write down. You just do V minus this. That's not too bad. And check that you actually get something perpendicular to this. Okay? Makes sense? So that's how projections work. You're just basically resolving something into a vector parallel and a vector perpendicular. And so there's a question on the homework that doesn't mention projections, but it says resolve into a vector parallel and a vector perpendicular. So that's what you're going to use. Okay, I have office hours now. Yeah, the next hour. So if you have questions. Otherwise, have a good weekend, everyone. Talk soon.